In this video, we're going to be talking about simple exponential smoothing, and these are the simplest of the exponential time series models out there. So typically, you would use these models when you look at the data and you're unable to figure out if there is any clear trend or seasonal pattern that exists in the data. So the data might look like it's all over the place. It might actually display some autocorrelation that is significant over time, but no trend or seasonal pattern. So this is where simple exponential smoothing methods work great. And you can always build on simple exponential smoothing models to add trends and seasonal components if you see that the data exhibits that. Now, the simple methods, think about a time series Y, where you could have something like a naive model, which you're familiar with, the future forecasts or all future forecasts given the information set at time t. So here on the left side, we have y hat t plus h being our forecast horizon. And given the information set at time t, we're saying that all future forecasts equal the last observed value of the time series. So what this means is that you are giving the most recent observation, which was in the previous period, all of the weight. So if you notice, yt has a weight of 1, right? So all of the weight goes to the last observation, and the past values, which is yt minus 1, yt minus 2, and so on and so forth, receive 0 weight. So you don't have you basically have a naive method that assumes that the most recent observation is the only thing that matters, the only important thing, and all previous observations provide no information for the future or for forecasting. So this can be thought of as a weighted average where all of the weight is given to the last observation. The other type of forecasting or simple exponential method is looking at average forecasts, where you can imagine the future values or the forecasts y hat t plus h given the information set at time t equal the average of the time series. So if you think this is just the mean of the time series or the unconditional mean of the time series. So here you have each observation being given equal weight or equal importance. So in this type of method, all future forecasts are equal to the simple average of the observed series. And we probably want something between these two extremes, right? So we don't want all of the weight given to the last observation. We also don't want equal weight being given to observations across time or in the past. We probably want something like where some scenario where more recent data actually has more weight and past data has less weight. So we want to understand how we're going to be able to do that. One idea here is that we think about alpha being the weight on the last observation, and then all other past observations have some weight attached to it, but there is an exponential decay of the weights for older observations. So alpha strictly lies in the 0-1 interval, as you can see here, and you can think about, let's say, you forecasting one period ahead in this case, and that being a weighted average of all of the different observations in the past, but the highest weight being given to the last observation, and then there is a decay that you see. So this is somewhat like, while this is an exponential decay, this is something like a geometric series. Now let's take a look at what happens if you have different values for alpha. So if alpha is equal to 0.2, you might have a very slow decay, which means that if alpha is 0.2, which means that the last observation yt receives a weight of 0.2, the way in which the weights decay is a lot slower. So yt minus 1 gets a weight of 0.16, yt minus 2 gets a weight of 0.128, and so you're seeing that there's not much difference. We have to really go back further for it to tend to 0. So you can see these tables where alpha is equal to 0.4 and alpha is equal to 0.6. The last column here represents a case where alpha is equal to 0.8, where we have very fast decay of the observation. So you have a weight of 0.8 assigned to the last observation, and notice that for yt minus 1, now you're assigning a weight of 0.16, which is significantly lower than 0.8. So you would have, this might actually be true for financial data, for example, where if the efficient market hypothesis holds, you probably are deriving much of the information from the last observation and very, very little information from past observations or observations prior to YT. Okay, so you have different values of alpha, and we'll see how that works for our forecasting exercise. Now, there are different types of ways in which you can express exponential models. One way is to look at a component form. This is a different representation for exponential models. There are different ones, but this is one of the ways in which exponential models are expressed. So for simple exponential smoothing, the only component included in the forecast equation is LT, which is governing the level of the time series or the smooth value. So the level or the smooth values of the time series at time t. Typically in the component form, you would have a forecast equation and a smoothing equation. So the forecast equation is going to tell you how the forecasts relate to the level of the time series, or if there were other components. In this case, we don't have seasonality or trends, so we don't have that here, but you have just a simple forecast equation. And then you have a smoothing equation, which is telling you how the level of the time series depends on the observed value of the time series itself and the past value of the level, right? So this is some sort of a weighted average here. The forecast equation, if you want to move this one, if you want to write this out for, just what the exponential model might look like, if we were thinking about a 1 period ahead forecast, then that is y hat t plus 1, given all the information at time t, and that would be equal to some sort of a weighted average between the observed value at yt and the fitted value at time t. And so if you would like, you can try this at home. This is also there in your book. If you iterate on this to get a moving average form, you would actually end up with an equation that looks like this, where the forecast at time period 1 is going to be equal to a weighted average between past values of yt and the initial level of the time series, which is L0, which is to say what is the level of the time series at time 0. And as the time series gets bigger and bigger, or as t tends to infinity, then you have a scenario where this last term tends to 0. Okay, so when we think about using simple exponential models and we want to solve for what are the optimal values of our parameters, we want to choose the optimal values for alpha and the initial level, right? So we don't know what the initial level of the time series is, but we have all this data. And we also want to know what the smoothing parameter is for the level of the time series. So in this case, we choose a method that's very similar to what we do in regression analysis. We choose to optimize by minimizing the sum of squared errors. The sum of squared errors in time series is going to be equal to the observed value, which is yt, minus y hat t, given all the information at t minus 1. So this is the fitted value of the series, given whatever model you're using. You square it, so this is like you're squaring your residuals and you are minimizing the sum of squared residuals or errors. Okay, so errors because you haven't estimated the model yet, but you are subjecting this method to the restriction where alpha is going to lie in the 0-1 interval. Okay, so because regression analysis has closed form solutions, in this case you don't have that, and so we use numerical optimization techniques. In particular, we use nonlinear minimization. So we're going to take a look at an example with Algerian exports where if we do optimize, we end up with a value of alpha, which is 0.84, and L naught, which is, or L0, which is 39.54. Okay, so the hats here denote that we've actually estimated the model, and these are the values that were reported from the model itself. Now, before going into how we code that, it is important to look at what this graph is telling us. So you have time on the x-axis, and you have exports as a percent of GDP for Algeria, and the black line denotes the original level. Okay. Now, if you did fit a model, a simple exponential smoothing model, to this data, because you thought that this data actually looks like it's all over the place. We don't know if there's a clear trend or seasonality. Definitely not seasonality. The trend seems to be also all over the place. Maybe in the last few years we see this kind of an inversion. If we were just focusing on this subsample right here, maybe we can do something, but really if you look at the entire time series, it's all over the place. So the simple exponential smoothing models is a good way to go when you look at the data and it looks like this. It's haywire. So you have the black line, which is your original data, and then you have these fitted lines that you see for the red line, the blue line, and the green line, which are fitted lines for different values of alpha. So let's take a look. If alpha is equal to 0, we're basically saying that the fitted series is going to look very smooth, and the level of the series would never update. Okay, very similar to what we were saying in the first couple of slides for this chapter. So what you have here is saying that the unconditional mean or the simple average of the series is just below 30% for Algeria, and if we were to forecast using alpha equals 0, then you would have some sort of a flat forecast going ahead. If alpha is increased to, let's say, 0.84, and we estimate or we plot the fitted line, then it's the green line. And if alpha is 1, which is similar to our naive or random walk model, where we're saying that the level updates completely, the series is definitely not smooth. So for higher values of alpha, you notice that the fitted values track the data much more closely, and these are not smooth. So this can actually help us. The value of alpha can actually help us track the data a lot better. Now, there is a difference between models and methods. So in the 1950s and 60s, with Holt, Brown, and Winter's work, you had algorithms that returned point forecasts for exponential smoothing methods, and those were methods. So we didn't really know about statistical models, but in the last 2 decades, there has been so much more innovation in state space modeling that have given us information on forecast distribution. So now we don't just have the point forecasts, but we also can generate forecast distributions. This has an advantage where the stochastic or random data generating process that is generating an entire forecast distribution can allow for proper model selection. You know, when you're reporting point forecast, what is the uncertainty associated with each point forecast. Okay, and you'll be able to see this in an example. Now, when we think about taking that model that we had earlier, the simple exponential smoothing method, we have these are called ETS methods, as I had mentioned in the previous video. The code that you're going to take to R is going to be called ETS, and you're going to associate the first term here with whether the error term is additive or multiplicative, okay? Whether the second term, which represents the trend, is going to be either none or additive or something else, okay? And the last term is seasonality. So these three different components are being represented here, and there's numerous combinations that you can imagine that can come up here in your code. So when we're thinking about a simple exponential smoothing method, we are going to make our error additive, okay? This is going to control the level. Of course, because we saw no trend and seasonality in our data, we're going to say no to trend and seasonal components, okay? So here you have the forecast error from this model, which is just YT minus, really this is your residual, it's not really your forecast error, but it doesn't matter when we're thinking about just looking at how well the data fits, sorry, how well the model fits the data. You have ET equals YT minus the fitted value of YT, okay, which can be written as YT minus LT minus 1, okay. You can manipulate this series into writing this in an error correction form as well, okay, which you can easily derive. Now, when we specify a probability distribution for ET, we can assume that this is normally identically distributed with mean 0 and variance sigma square. Okay, so we'll look at an application of this in the next video.